Hello and good day everyone. This short video created by instructor Tom Kennedy of Milwaukee Area Technical College and member of IBEW Local 494. The information presented in this video is aligned with the Electrical Training Alliance Blended Learning Management System. Specific information included is to accompany the AC Theory Level 1, Lesson 1 of the curriculum. The learning objectives covered in this lesson are: define inductance and self-inductance. Define counter-electromotive force using Lenz's law. Identify the physical factors that affect inductance. Explain the behavior of current in DC circuits when inductance is present. Describe the relationships among current, applied voltage, and counter-electromotive force in inductive circuits. To review, previous lessons have given Faraday's law that if a conductor is moving relative to a magnetic field, a voltage will be induced into that conductor. Therefore, three factors need to be present to achieve this induced voltage: a conductor, a magnetic field, and relative motion between the conductor and said field. The voltage polarity and direction of current can be influenced by the direction of the conductor, magnetic field, and the relative motion. This is expressed using Fleming's left-hand rule. When evaluating the circuit using electron flow theory, the thumb indicates the direction of relative motion of the conductor to the magnetic lines of flux. The forefinger points in the direction of the field flux, and the middle finger indicates the direction of current that will be induced into the conductor. The amount of voltage and current created in a circuit is dependent on three additional factors: the active length of a conductor moving relative to the magnetic field, the strength of the magnetic field it moves through, and the speed at which this interaction occurs. When a conductor has a voltage applied, it will develop a magnetic field about the conductor. The strength of this magnetic field is proportional to the amount of current that flows through the conductor. The magnetic field direction around the conductor can be determined using the left-hand conductor rule. Using electron flow theory, placing the left hand around the conductor with the thumb in the direction of the current through the conductor. The fingers will indicate the direction of the field flux present around the conductor. What is an inductor and how does it generate inductance is what requires overview at this point. Inductors are passive electrical components consisting of a coil, turns or wraps of wire, which is designed to take advantage of the relationship between magnetism and electricity as a result of an electric current passing through the coil. This is accomplished simply by taking a wire and wrapping it into the shape of a coil, so the magnetic fields around the conductors interact with each other. The schematic symbol for an inductor represents that of a coil of wire. Inductors usually are categorized according to the type of inner core they are wrapped around, for example, hollow air core, solid iron core, or soft ferrite core. The different core types being distinguished by adding continuous or dotted parallel lines next to the wire coil as shown. An inductor that is shown with an arrow through the coil represents a variable inductor, where the value of the inductor can be changed by adjusting the inductor in some way. Inductors work under the premise that when a changing voltage or current is present in the conductors, the magnetic field around the conductors will interact. Induced voltages will be created in the conductors that are adjacent to one another within the coil. This induction of voltage is known as counter-electromotive force or CEMF. This can be also referred to as back EMF. Consider the image on the right as an expanded view of the coil in the circuit shown in the schematic. Evaluate a single turn of the coil with respect to the adjacent turns. When the switch is closed, the voltage will be applied to the inductor. The magnetic field is expanding as the current tries to reach its maximum when the voltage is applied. The adjacent turns of wire are moving relative to the expanding magnetic field of the conductor that is shown in the image. Since there is relative motion, a magnetic field in the conductor, a voltage is induced based on Faraday's law. Fleming's left-hand rule can be applied to the adjacent conductors to the conductor shown here. The polarity of the voltage that is induced into the coil is the opposite direction from the applied voltage. This creation of counter-electromotive force when a change in voltage occurs is known as inductance. The amount of counter-electromotive force that is created by the interaction of magnetic fields is directly proportional to the change of applied voltage that produced it. This is known as Lenz's law. Therefore, a statement can be made that inductors always oppose a change in current. If shown as vectors, a statement can be made that CEMF is always 180 degrees in direction to the applied EMF. This makes them effective at slowing down or eliminating surge currents when voltage spikes occur. Therefore they have the name, choke. The inductor will choke off a surge current. The counter-electromotive force of an inductor is given a value of inductance. The formula letter designation of inductance is abbreviated L. The specific unit associated with inductors is the Henry. This unit is named after the American physicist Joseph Henry, who is credited with discovering electromagnetic induction about the same time as Michael Faraday. The unit of inductance that is given the value of 1 Henry is when 1 volt of counter-EMF is created when a change of 1 ampere in 1 second is applied to the inductor. The physical factors in the construction of a coil or inductor that affect the amount of inductance a coil will have are related to the factors that are identified in Faraday's law. The amount of voltage induced into a conductor is proportional to the active length, the strength of the magnetic field, and the speed of the relative motion of this interaction. Therefore, the number of turns, cross-sectional area, core permeability, and length or turn spacing are factors that affect inductance. The number of turns will determine the active length of conductors interacting in adjacent magnetic fields of other turns. The cross-sectional area of the coil, the larger the diameter a coil has or cross-sectional area, the amount of conductor needed for each turn will be longer for a larger cross-sectional area. A longer conductor will result in more active length interacting in adjacent magnetic fields of other turns. The core permeability, the material present in the core of an inductor, will condense or focus the magnetic field flux, thus the strength of the magnetic field will increase when a ferrous core material or material with a high permeability is used. The core length or turn spacing, as previously learned about magnetism, the strength of a magnetic field is inversely square to the distance from the source of the magnetic field. If conductors are spaced closely together, the magnetic fields that are interacting are stronger than if conductors are held farther apart. Therefore, the length of a coil is inversely proportional to the amount of inductance a coil has. The formulas shown here can be used for reference to determine the Henry value of a coil of a perfectly helical coil if the factors that affect inductance are known. Evaluating only the coil of this parallel circuit. When the switch is first closed in this circuit, the applied voltage in this example is 12 volts across the inductor. The 2 ohms of conductor resistance of the inductor will limit the total current in this portion of the circuit to 6 amperes. The 6 amperes does not happen instantaneously when the switch is closed. The expanding magnetic field about the conductors of the coil will generate counter-EMF, which will oppose the voltage that is applied. Lenz's law states that the amount of CEMF developed will be equal to the initial change in voltage. A DC circuit will go from 0 to 12 volts applied across the inductor instantly when the switch is closed. The expanding lines of flux will create CEMF as the expanding magnetic field interacts with adjacent conductors. As shown with Fleming's left-hand rule, this CEMF will limit the amount of current in the circuit during the period that the magnetic field is expanding. Since the applied DC voltage is a steady-state application of potential, the magnetic field about the conductors will cease movement, and therefore the opposing counter-EMF will decay. At the end of the magnetic field expansion, the total current will get to 6 amperes until the circuit is turned off. The graph shows the timeline of the applied voltage, counter-EMF increasing to a peak and decaying, with the resulting current increasing to its maximum of 6 amperes. When the switch is opened, the reverse situation will be similar to energizing the coil. The magnetic field about the conductors will begin to collapse. The direction of relative motion of the adjacent conductor now reverses and creates CEMF opposite the change in applied volts. The current will now be induced into adjacent conductors in the same direction as the original applied current. This will cause current to continue to flow in the circuit until the CEMF developed from the changing magnetic field decays to 0. Since counter-EMF is present when a DC voltage is applied to an inductor and is also created when the voltage is removed, the ability to quantify how long the current will take to get to its maximum value can be calculated using what are called time constants. Every conductor has some resistance. This resistance will oppose the current that flows to establish the change in magnetic field, regardless of the amount of resistance and inductance. The rate at which the circuit increases to maximum value will always follow a specific pattern. This natural pattern is associated with Euler's number. The magnetic field expanding and contracting around a conductor is based on the inverse square law. Therefore, the value of increasing current or decaying CEMF is an exponential rate of change. The interaction of these magnetic fields are given by the value of inductance in henries. The CEMF created by a coil when a DC voltage is applied will decay at an exponential rate as the magnetic field expands and slows to a stop. Euler's number can be used to calculate the values of these decaying voltages or increasing currents. Time constants are a method of determining exponentially increasing or decreasing values. Time constants based on exponential decay are e to the power of -1. E to the power of -1 is approximately 0.368 or 36.8%. Time constants based on exponential growth are e to the power of -1 subtracted from 1. E to the power of -1 subtracted from 1 is approximately 0.632 or 63.2%. Euler's number is an irrational number but can be approximated at about 2.71828. There are many additional videos you can find on YouTube to explain Euler's number in more detail. Time constants are periods of time created during exponential growth and decay that can be calculated with Euler's number. The time constants are a set period indicated by the Greek letter tau. The value of one time constant of an inductor can be calculated by dividing the inductance in henries by the resistance in ohms. Since the value of inductance and resistance are based on a unit of 1 volt, the application of Lenz's law and Ohm's law can be used to derive the formula for one-time constant. Isolating the change in time relationship per volt and substituting Ohm's law into the counter-EMF formula. A formula to determine the time it takes for one-time constant to be completed can be determined. This time constant formula would be the amount of time it would take to get to either 63.2% or 36.8% of the total value, depending on if the value is growing or decaying. During the application of voltage when the switch is closed for this circuit, the initial counter-EMF developed per Lenz's law will be -12 volts. As the magnetic field expands, the CEMF will peak at -12 volts. This peak CEMF will begin to decay as the magnetic field reduces the relative motion. Applying the time constant formula for the 0.2 henries divided by 2 ohms, the time constant period is 1/10 of a second. In 1/10 of a second, the CEMF will decay to a value of -4.42 volts, which is 36.8% of 12 volts. The value of CEMF can be considered as an opposing source of 4.42 volts. With an applied voltage of 12 volts and a counter voltage of only 4.42 volts. The applied net voltage will be approximately 7.58 volts. The net 7.58 applied volts acting on the 2 ohms of resistance will allow approximately 3.79 amperes to flow through the inductor. Evaluating the current using the exponential growth formula. The maximum current that will flow in the inductor when the circuit stabilizes is going to be 6 amperes. Applying Euler's number to the 6 amperes as growth. The value of current at 1/10 of a second will be approximately 3.79 amperes. Determining the value of current using either method results in the same value of current. Another time constant or the next 1/10 of a second time period, the value of counter-EMF will continue to decay. The resulting CEMF will be about 36.8% of the remaining 4.42 volts. The CEMF has now decayed to a value of about 1.62 volts. The resulting applied voltage acting on the resistance will be about 10.38 volts, which will allow about 5.19 amperes to flow. Looking at the current by itself at the first time constant, the value of current will be 3.79 amperes. The remaining difference in current will raise another 63.2% during the next 1/10 of a second. Therefore, after 2/10 of a second, the amount of current will rise to approximately 5.19 amperes. During the third time constant or after another 1/10 of a second, the value of counter-EMF will continue to decay. The resulting CEMF will be about 36.8% of the remaining 1.62 volts. The CEMF has now decayed to a value of about 0.6 volts. The resulting applied voltage acting on the resistance will be about 11.4 volts, which will allow about 5.7 amperes to flow. Looking at the current growth again. The remaining difference in current will raise another 63.2% during the next 1/10 of a second. Therefore, after 3/10 of a second, the amount of current will rise to approximately 5.7 amperes. During the fourth time constant, the counter-EMF continues to decay. The resulting CEMF will be about 36.8% of the remaining 0.6 volts. The CEMF has now decayed to a value of only about 0.22 volts. The resulting applied voltage acting on the resistance will be about 11.78 volts, which will allow about 5.89 amperes to flow. Looking at the current growth after 4 time constants. The remaining difference in current will raise another 63.2%. Therefore, after 4/10 of a second, the amount of current will rise to approximately 5.89 amperes. It should be noticeable now that the amount of change relative to time is becoming less and less as the CEMF decays to near zero and the current approaches 6 amperes. During the 5th time constant and the last one evaluated in this example, the counter EMF continues to decay. The resulting CEMF will be about 36.8% of the remaining 0.22 volts. The CEMF has now decayed to a value of about 0.08 volts. The resulting applied voltage acting on the resistance will be about 11.92 volts, which will allow about 5.96 amperes to flow. Looking at the current growth after 5 time constants. The remaining difference in current will raise another 63.2%. Therefore, after 5/10 of a second, the amount of current will rise to approximately 5.96 amperes. At this point, there is such a slight difference between the total current and the value determined after 5 time constants, it can be said that a circuit will be at maximum current flow at this point. The 5 time constant factor can be applied to the circuit as it is de-energized. The current will decay as the counter-electromotive force created in adjacent turns of wire decays. Since the induced voltage and current are in the same direction, they will decay at the same rate. It can be stated that inductors opposed a rise in current because of the counter-electromotive force created by the magnetic field is opposite the applied voltage. And inductors will continue to provide current at a decaying value when the DC source is removed. A small note, the circuit evaluated contained a parallel resistor. If this resistor was not present in the circuit and the switch were opened, the current would immediately stop when the switch is opened. The magnetic field about the coil would naturally dissipate into the Earth's or adjacent magnetic fields. The graphs shown are percentages of the total value for growth and decay when using time constants. Viewing the graph of the growing circuit. After the first time constant, the value would reach 63.2%. If one calculated another 63.2% of the remaining 36.8% and added it to the original 63.2% from the first time constant, the resulting value as a total percentage would be 86.5%. This is the value for the second time constant. This can be repeated for each time constant remaining. Remember that when determining the time required to achieve full current, that it takes 5 time constants to get there. If one needed to calculate a current of voltage value at a specific point in time that does not correspond to a time constant interval, the same formulas can be adjusted to take Euler's number to a power of the fraction of time compared to the time constant. So long as the time constant time is known using the L/R time constant formula. To review, inductors are components that use magnetic fields to create a counter EMF that oppose a change in applied voltage. Counter-electromotive force is an opposing force created in a coil when a change in the applied voltage occurs. The CEMF will limit the current during the period of change when voltage is increasing and will add current when voltage is decreasing. Lenz's law states that the direction of the current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field which produced it. An inductor is a passive electrical component consisting of a coil of wire which is designed to take advantage of the relationship between magnetism and electricity as a result of an electric current passing through the coil. Inductance used the letter L in formula designation. The unit associated with inductance is the Henry. The factors that affect the inductance of an inductor are number of turns, cross-sectional area, core permeability, and length or turn spacing. Time constants can be used to determine the time required to achieve maximum current in a DC circuit with inductors. After 5 time constants, the circuit is considered to be at its maximum or minimum depending on the application. Thank you for watching this video. You should be prepared to complete AC Theory Level 1, Lesson 1, but feel free to consult the textbook and LMS resource to aid you in completion of the online quiz.